presented by Caltech.
Good afternoon. I would like to welcome you all to the first lecture of the 2017 Everhart Lecture Series. My name is Kelly Mauser, and I'm the chair of the Everhart Committee. The Everhart Lecture Series is a program funded by the Graduate Office and supported by the Graduate Student Council. It is a forum that encourages interdisciplinary interactions amongst students and faculty and recognizes the exemplary presentation and research abilities of Caltech's graduate students. Each year, an interdisciplinary committee of fellow graduate students selects 3 lecturers based on their dynamic speaking skills, their ability to communicate the broader importance of their research field, and the impact of their work on the scientific community. As you all know, Caltech has an abundance of outstanding graduate students with all of these qualities, and choosing just 3 from this year's candidates was certainly no easy task. The first of this truly exceptional group is Goza from the Department of Mechanical Engineering. At this point, I would like to ask Professor Tim Colonius to come up and introduce Andre.
Thank you, Kelly. Let me add my welcome to everybody to the Everhart Lecture, and let me say how happy I am to introduce Andres Goza today. So Andre grew up in Brownsville, Texas, and he got his undergraduate degree at Rice University in 2011. He got an NSF fellowship to come to Caltech, but he elected to spend a year abroad, so he went to Cambridge University, where he studied fluid mechanics at the Department of Applied Mathematics and Theoretical Physics, or DAMT. And then he arrived at Caltech in the summer of 2012, and he's been working in our group since then on computing solutions to flow structure interaction problems. So he's going to tell you about one of those problems today. So in addition to having been awarded an NSF graduate fellowship, Andre's been a very productive student at Caltech. He's published 2 papers in the Journal of Computational Physics, and he is preparing several more manuscripts right now. He aims to complete his PhD in the fall. But I have to say that the most amazing thing about an amazing student like Andre is that he has really the best sense of humor of many students that we've had in the group, and so I couldn't prepare this introduction without wanting to share some humorous anecdote from our 5 years with him. And the thing is that in thinking back on these anecdotes, I couldn't think of anything that would be appropriate to share publicly. And so I could only think of one to do, and it's an inside joke. So I may lose the audience on this, and I may annoy the audience with this, but let me just say, ladies and gentlemen, Andres Goza.
Thanks, Tim. Well, after a glowing introduction like that, I guess the only thing to do is to present at this point. Sorry, I forgot to plug in this laser pointer here. Okay, well, thank you, Tim, for that those very kind words of introduction. So this is going to be a really fun talk, and it's about a really beautiful dynamical system that involves inverted flag flapping, as is indicated in the title here. And so the way that I want to contextualize this is, if you're anything like I was not so long ago, the phrase inverted flag means very little to you. And so I want to start off by talking about conventional or kind of standard flags and what those look like in terms of the fluid mechanics community and why the fluid mechanics community is interested in standard flags. And then we'll use that as context to go into inverted flag flapping and why we're interested in that. So that's kind of the general roadmap for today. So what does standard flag flapping look like? My hope is that you have an image of wind blowing past some flagpole that has a flag attached to it, and the flag starts flapping, right? And so to give you an image of what that looks like in the kind of ways that fluid mechanicians like to think about that, I'll show you a video from one of our simulations. So we've got wind or some fluid coming from left to right, and as it does so, it makes this flag, which is highlighted in green here, bend and deform. And what we're looking at here is a 2-dimensional cross-section of a flag. So the flag is coming in and out of the slide here, and we're looking at some slice. And as the flag flaps, you can see that it's generating these beautiful structures downstream of the flag. And what I'm showing here are contours of something that's called vorticity. So vorticity is a really important quantity in fluid mechanics, and it essentially measures the amount of spin or swirl that we have in a fluid. So what we're looking at here is as the flag is flapping, it generates these patches of fluid that start swirling, and then they get carried downstream by the fluid as they do so. And I'm indicating through the different colors the sense of swirl that you're seeing. So these follow the right-hand rule. So let me see if I can remotely get this right. So positive is this way. So red is spinning like this, and blue is spinning like this as it comes this way, right? So, whoops. So that's what this problem looks like in the kind of fluid mechanics world that we like to think of this. So that's a flapping flag, and my hope is that that's familiar to you. Why do we find it interesting? Well, the main idea here is that as this flag flaps, it bends and deforms, and that deformation is associated with some strain energy, right? So the fluid is putting energy into the flag, which is being stored in the flag as a form of strain energy. And there are a number of ways, for example, using a piezoelectric device to convert that strain energy into electricity. And so the idea here for these flapping flag type systems is, can we develop some kind of renewable energy harvesting strategy? I just kind of want to zoom in on this for a second and say that this isn't some kind of pie in the sky idea. There's really research going into trying to understand how we can enable this type of technology. And to give you an example of that, I'd like to highlight something that was done by a colleague of mine, Felipe Tosi, in collaboration with the NASA Jet Propulsion Laboratory. And after a series of iterations, they came up with the following energy harvesting design from this kind of flapping flag idea. So what you're seeing here is fluid is moving past this caged enclosure into this nozzle geometry. And as it does so, it gets this flag that you see here into this kind of flapping vibration. And the flag is connected at its base to this enclosure, which contains a set of piezoelectric stacks that are vibrating and sort of humming with the flag. And as they do so, they're generating electricity. And after a series of iterations and experimentations, Felipe and his collaborators at JPL saw a power output of around 0.1 watt. So that's very modest in the scheme of large-scale energy harvesting. So this is nowhere near the type of power capacity that would be able to provide power to rural communities or really anything that's relevant for the developed world. But there are two things that I want to highlight here. The first is this power capacity that Felipe and his collaborators found is over an order of magnitude of what anything else that we saw in the literature so far. And so for me, that opens the question about how much power are we leaving on the table, right? So the fact that through experimentation and iteration, we're able to do an order of magnitude better in power production than what anybody else has seen, for me asks the question of, if we can understand this system more systematically and really sink our teeth into the physics, then maybe we can identify upper bounds for what power capacity and energy harvesting potential is for these systems, and guiding the design of systems that can achieve those upper bounds or get close to them, right? So that's one thing that I'd like to highlight. And the second is, even at this modest power capacity that we're seeing, that's already relevant for some niche but important applications, right? So there are, for example, remote sensing networks in Antarctica, for example, that gather data about global warming. And these remote sensor networks are within the power range that could be obtained by putting a small array of these devices together at this power generation capacity. So I think in the near term, there are already some exciting applications that we can access. And in the long term, I think there are really interesting physical questions about how far can we take this? And that's kind of our motivation for looking into this kind of system. OK, so I've motivated all of this in the context of this kind of standard flag problem that we're more familiar with. So I'd like to change gears and go into the inverted flag problem and talk about why we find that interesting. OK, so here I'm showing a video that's analogous to what we showed before, what we saw before. But now we've got an inverted flag. So the difference between this inverted flag and the standard flag that we saw earlier is, instead of pinning the flag at the leading edge, which is what you saw before, now we're clamping it at its trailing edge. And you can see that just by changing where we've clamped this system, we're completely changing the dynamics, right? So if you look in the fluid, those vortical structures that we saw earlier are completely different in size and in character and in the way that they move downstream. And the flapping behavior of the flag is also very different. So what we want to ask is, can we understand the physics of this inverted flag system, again, in the spirit of trying to understand these energy harvesting flapping flag systems more generally? So I'll talk about this in the context of the inverted flag, but the idea is kind of building up a framework to understand these systems more generally. OK, so I'd like to study the system in two ways. The first thing that I'd like to discuss is everything that we do in Tim's group, for the most part, and everything that I do in Tim's group involves numerical simulations. So these all come from data that is run using code that we create in-house. And so the first thing that I'd like to talk about is what are the challenges of being able to simulate these problems in the first place? So what tools do we have to develop? It turns out that simulating these problems in the first place is still an active area of research. So I'd like to talk about what the challenges are there and the ideas that Tim and I have come up with to address those challenges. And then we'll go into the physics of the system and trying to probe what's happening for these types of systems. OK, so that's kind of our roadmap. And I'd just like to highlight that the reason that we're interested in inverted flags as a candidate is that you can see that they undergo larger amplitude bending than in the conventional flag case. And so a kind of natural question and hypothesis that we might make is, are they better candidates for energy harvesting technologies? So we're not going to answer that question now, but that's the reason that we're interested in this. And again, we're interested in studying this system more. OK, so I want to go into the math now and talk about what the challenges are for simulating these types of problems. So the main challenge for this revolves around the fact that there's what we call fluid structure coupling. So the idea is that as flow is moving, or your air or wind or whatever it is moving from left to right, then it affects the motion of the flapping. And it causes the flag to deform. But then as the flag starts deforming and starts flapping, then that in turn affects the motion of the fluid. So there's this coupling between the fluid and the flag or the structure that exists. And it turns out that that coupling mathematically is nonlinear. So treating that in an efficient way is a very difficult thing to do. And so what I'd like to do to talk about the math side of this and how we approach this is introducing the equations and talking about how different people in the literature solve these equations, and then ultimately the idea that Tim and I came up with to try to solve these in an efficient way. So that's kind of where we're going. And in order to talk about how we solve the equations, we need to talk about what the equations are, right? So that's what we're going to do. And essentially, there are three equations at play here. There are the fluid equations that govern how the fluid flows. There are the flag equations that say, given some forces on the flag, this is how it will deform and move. And then there's a really important constraint, which is a boundary condition, right? So the fluid can't just move however it wants to. It has to move in a way that is consistent with the way that the flag is moving. And the boundary condition is what encodes that information. So the way that this works is this boundary condition is a condition on the interface or surface of the flag. And what the boundary condition says, we call this the no-slip condition in fluid mechanics. And what it says is that the velocity of the fluid at this interface must be equal to the velocity of the flag at that interface. I'm going to make a confession here that I hope Tim doesn't judge me too much for, but that took me a very long time to conceptualize in my heart. And so I'd just like to talk through why that no-slip condition exists. And the idea behind this is actually quite intuitive, right? If you have a flag that's like this, in this position, and it starts to move up, then the flag is not porous in this case, right? It's a solid flag. The fluid can't move through the flag. It can't do anything but move with the flag as the flag is moving. So that's the boundary condition that says that the velocity of the fluid must match the velocity of the flag at that flag surface. And that is what encodes the communication between these fluid equations and these flag equations. So that's kind of how that works. So we're about to go through the mathematics of how this works from a high level, and I'd like to justify for you why we're going to do that. And the reason is, I know that not everybody feels this way, but frankly, I love math. And I know that not everybody does, but I want to show you math because I think it's beautiful. And I don't need to convince you, if you don't believe that math is beautiful, that it is beautiful. But I would like for you to try to stick with me, and my goal is that by the end of this, we can feel really comfortable from a high level of how these equations work and how they're solved. And if so, I think that would be a really great accomplishment and my attempt to convey some piece of why I think math is beautiful and why I love it. So anyway, that's my motivation for it, if you're allowing me a cheesy aside. OK, so the framework that we're going to build this mathematics in is the following. So we're going to start by saying we know exactly what the flag and the fluid are doing at some instance in time, right? So let's take this snapshot. Let's say at this moment in time, I know exactly what my fluid is doing, and I know exactly what my flag is doing. So I know the velocity and position of the flag. I know the velocity and pressure of the fluid everywhere. And I want to ask myself the question, at some small instant in time later, what happens, right? And if we can solve that question, then we can simulate these problems, because we can just keep moving forward instances in time until we're done simulating, and we're happy with having simulated as far as we have. OK, so that's going to be the context for this. So let's write down these equations. So I'm writing these equations in an abstract way, and we're going to kind of talk through what they mean. The way that I'm writing them is like this. So we have a set of fluid equations here, which I'm associating with this script f. And what these equations are saying is that I have a set of fluid unknowns. So the unknowns here are x. X means an unknown. And the subscript f means it's an unknown associated with the fluid. And all that this equation is saying is that that unknown, those fluid unknowns, have some functional dependence. And the function is associated with the fluid. So it's given the subscript f because it's a fluid function. And it's a function both of the unknowns in the fluid, which we don't know, and of the structural unknowns, which I'm calling x sub s. So I'm using an S because I can't use F for fluid and flag. So I'm using S for structure, and I hope that you can follow me with that. OK, so this is very abstract. And when I wrote it down the first time, this is not the way that we normally write the equations. And so I looked at this and was like, what is this saying? So let's talk through it for a second with an example. So the example is here. So let's just consider the linear equation y is equal to 3y plus 2, right? We can solve that equation for y if we want to. And we can also just write this right-hand side as some f of y, right? It's some function of y. So there's an equation that looks kind of like this equation, right? We have a y equals f of y. So this is kind of a trivial example, and we can very readily solve for y. But let me show you one that is a little less trivial, right? So we can look at another example that, again, has a y equals f of y structure. But now the f of y is nonlinear. And perhaps there are people in the crowd who could do this, but I could not personally solve this equation for y. So you can see how things get more complicated by just introducing nonlinearities in this function. So these are some kind of simple examples that give us a sense for what this equation looks like. But I'd like to highlight some distinctions between either of these equations and the one that I'm showing up here. So the first distinction is that this is a function. This is an equation for just a scalar y, right? Just one variable y. And these boldface variables denote that they are vectors. So we don't have one unknown here. We have a vector of unknowns. And so rather than having to solve one equation, we're having to solve a series of very large dimensional equations. So that's one complexity. And another complexity is this is y is equal to f of y. But here we have an unknown, which is a function of that unknown, xf, but also of xs, right? And so there's this coupling with another term that adds to the complexity of it. So from a high level, these are what the fluid equations are, and that's what I'm trying to convey to you in this equation. So there are also a set of structural equations, which again, there's flag or structure, which I'm denoting with an S. And I've written them in an analogous way, right? So we have an x sub s. And this has some functional dependence that is a function of, that is representing the fact that it's associated with the structural equations. And it's a function both of the fluid unknowns and of the structural unknowns. And the last thing, as I mentioned, is there's a boundary condition. And what this equation is saying is I'm taking the fluid velocities on the surface of the flag, and I'm requiring that they be equal to the velocities of the flag on the surface, right? So that's what that boundary condition is saying. OK, so my hope is that there's some intuition here for what I mean when I say that what these equations are. So the next thing that I want to do is look into some common approaches in the literature for how we solve these equations, and then talk about the modifications that Tim and I have made to try to make that process more efficient. So the first approach that people use that is common for solving the system is called the block Gauss Seidel procedure. So what I've shown here is I've reproduced the equations that I showed you in the last slide. So my hope is that these are familiar to you. And the idea with the block Gauss Seidel procedure is we say, you know, I have a very good guess for what my flag is doing because I know my system an instance earlier in time, a very short instance earlier in time. So why don't I use my flag unknowns, xs, from my previous instance and plug those in to this equation here, and then solve my resulting equation for xf. So it turns out that when you plug in an xs, you can solve this for xf. And that's the idea behind the block Gauss Seidel procedure. And you say, OK, now I have a guess for xf, so let me use that to update my flag variables xs. So I plug xf in here, and it turns out that you can solve this equation for xs once you have xf. So that's the idea behind the block Gauss Seidel procedure. It's kind of simple in nature and intuitive in many ways. But one caveat to that, right, is we never accounted for the boundary conditions that have to be satisfied when we did that iteration. So there's no guarantee that they will satisfy those boundary conditions at all because we didn't ask them to. So the next step in the block Gauss Seidel procedure is to plug in our new xs and xf into this expression and ask, does it satisfy that boundary condition? And if it does, then fantastic, we're done. But if it doesn't, then we have to go back into this loop and say, OK, well, now I have a new guess for xs that came from my latest guess for xf. So I'm going to plug that back up here into this expression for xs, solve for xf, and so on we go, right? So that's the idea, is you keep iterating until you arrive at a set of fluid and structure unknowns that satisfy both these equations, but also the boundary condition. So that's kind of a high-level schematic of how this block Gauss Seidel procedure works. So what are the pros and cons? The pros are that it's very easy to implement this approach, and it turns out that performing one of these iterations can be done very quickly. So it's very cheap to perform one iteration. But the downside to this is that oftentimes you need to perform many, many iterations in order to get this to converge. And so you kind of are getting hurt because even though it's easy to perform one iteration, you have to perform many of them. So that's the downside. And in fact, in many cases, this approach won't converge at all, right? So there are questions of robustness and of efficiency in how to get this procedure to converge effectively. So what I'm going to show you next is another approach that has sort of the opposite sets of pros and cons. So the pros will be that this thing converges in a very small number of iterations. But the cons will be that it is very costly to perform one iteration, right? And you might deduce that the idea that Tim and I had was, can we kind of have our cake and eat it too? Can we have fast convergence behavior and do it in a way that it's cheap to perform one iteration? So that's kind of where we're ultimately going. But for now, here's the second approach. Oops. Oh, great. For now, here's the second approach. So again, I'm rewriting these three equations from before, these equations that we need to satisfy. And the idea with Newton-Rapson is to take account of the fact that we have information in these equations that are telling us what our next guess should be. So rather than just plugging in a guess from the last instance in time and saying, OK, I want to plug that into here and just start going round and round, can we use information from these equations to get a better guess for what our next update should be, right? So that's the idea. And the way that we do this is we say, well, these are nonlinear equations. And so it's difficult to solve these all at once. That's kind of the whole point, is they're difficult to solve. But maybe we can linearize these equations about a really good guess, for example, our guess at the last instance in time, and use that as, and solve that linear equation to update our guess. So what does that look like? So we want to linearize this, and I want to give you some intuition for what that might look like. So here, I'm plotting this nonlinear function that we showed earlier. So this is the f of y is equal to y to the fourth plus sine y. So before, when we were looking at that y is equal to f of y, this is the nonlinear f of y that we saw. And I'm plotting this as a function of y, right? So you can see that this is nonlinear, right? You can't fit this with one line. And so if I wanted to solve y is equal to f of y, that would be a difficult thing to do. But if I had a very good guess for what y is, and in these equations, we do have a very good guess for what our solution is, because we know the solution at the last instance in time, then we might say, well, I think that y is going to be very close to this value. And so what we say then is, over this regime, over this range, maybe we can fit it with a line. So this f of y is not a linear function, right? And you can see that the line that we use to fit this does a terrible job of representing f here or anything like that. But if we're near enough to our initial guess, then maybe we can solve y equals f of y with f replaced by this linear function, right? And now that becomes something that is much more tractable. So that's the idea behind what we want to do here. We're doing exactly the same thing. We're linearizing about our solution at our last time instance and solving the whole linear equation. So that's a way of creating something that is linear, which makes it easier to solve, but it's still linear, a linear representation of all of these equations, right? So it's conveying information from all of these equations for us. So that's the idea behind Newton-Raphson. So when we linearize this particular system, it looks like this. So we have a matrix system that is essentially AX equals to B. And in this case, we have B, which is a right-hand side that is known. We've stacked our unknowns, x sub f and x sub s. And we have, in the top row, the equations that correspond to the fluid unknowns, and in the bottom row, the equations that correspond to the structural unknowns, okay? And what you can see is that xf gets multiplied by aff. So this is the contribution that the fluid unknowns have on the fluid equations. And here, we have this contribution. This gets multiplied by xs. So this matrix represents the impact of the structural or flag unknowns on our fluid equations, right? So we have this coupling that the fluid unknowns and the structural unknowns have on one another. And that makes sense because coming back to this linear equation, we know that these fluid unknowns are determined both from the fluid unknowns and from the flag unknowns. And so this cross term reflects that. And we see the same thing in these flag equations, right? So we have these bottom set equations for the flag. And again, there are contributions that the flag or structure has on itself and that the fluid has on the flag. So we come up with these linear system of equations. And the mechanics from here are kind of similar to the Bloch-Gauss Seidel procedure in that we iterate. So we solve this linear system of equations for our unknowns, xf and xs. And when we do that, then we ask ourselves, does it satisfy the boundary condition? So it needn't, right? We solved a linear set of equations to arrive at this solution. And we hope that it's a better guess, but there's no guarantee that it will exactly satisfy our boundary conditions. So if it does, then we're done. But if it doesn't, then we have to come back. And we now linearize about the latest guess that we just got for our fluid and our structure unknowns. And then we solve this linear equation again, and we keep iterating until we have something that solves all of our equations, our fluid equations, our flag equations, and our boundary condition. OK, so what are the pros and cons of this? The pros are that typically this approach converges quite quickly and has much more robust behavior than the Bloch-Gauss Seidel procedure. But the downside is, to update our guess for our fluid and flag unknowns, we have to solve a very large linear system each time. And so we're taking a huge hit in having to do that. So the question that Tim and I asked is, can we reap the benefits of having a small number of iterations that come from linearizing the system, but can we avoid having to solve such a large linear system in doing that? And that was kind of our idea here. And our approach is a Newton-Raphson approach. So I'm showing our approach here. And again, we've got our equations from before, and we linearize them to arrive at this linear set of equations, which is large and costly to solve. And the way that we do this, if you're not familiar with LU factorization, then unfortunately I don't have time to explain it to you. But the punchline is that we're able to rearrange these equations in a way that we can decompose them such that we can solve them analogously to how we approached the first problem, to how we did our Bloch-Gauss Seidel procedure, right? So we came in here, and rather than having to solve this large linear system of equations, we can actually decouple them and solve them separately. So we have this equation for the fluid unknowns here, and then we have this equation for the structural unknowns separately. So what this is telling us is that when we iterate, we're iterating based off of a linearization of the system, and so we get the same convergence behavior. This is literally the same approach as this Newton-Raphson procedure that converges quickly. But performing an iteration can be done in this efficient way that allows us to decouple these equations. So that's our idea for how we ended up wanting to solve these. OK, so thank you for sticking with me. I hope that that made some sense. And if not, I'd be happy to talk about it after, or yeah. OK, so now we have our tool that will allow us to simulate inverted flag flapping problems. And so now we want to come back to that system of this flow past an inverted flag. So this is the result of that algorithm that technique that I just described to you. And so we want to come back to this problem and ask ourselves, what is the physics of this? And we're going to look at the physics of this with respect to two specific parameters. We're going to look at varying the mass of the flag and the stiffness of the flag, and we're going to ask ourselves, how does the behavior change as we do that? So let's talk about how we define those parameters, the mass and the stiffness. So the mass of our flag looks like this. And I've written this in kind of a funny way. This is a very common thing to do in fluid mechanics. It's called a dimensionless parameter. And what we're doing when we write this dimensionless parameter is we're taking, in the numerator, the dimensional flag mass. So this is literally the mass of the flag. And we're normalizing it by some inertia or mass in the fluid. And the reason that we like to do that is the following. So let's say we want to run a set of experiments, and we run a set of experiments in air for a variety of flag masses. And then we change our fluid, or we change the mass, well, no, let's say we change the fluid from air to water, right? Then how will our results change as we change the mass of the flag? They will certainly be different than what we saw in the first case. And there will be a variety of reasons for it. But one reason is that the mass of the flag is not important unto itself. It's important with respect to how it changes with respect to its ratio in the fluid, right? So this is a way of saying, if we keep all other parameters fixed, and we allow ourselves to change not just the mass of the flag, but the ratio of the mass of the flag to the fluid, then keeping that constant will allow us to see the same behavior. So it's a way of allowing us to keep the physics constant. That's why we like these non-dimensional parameters. So if that was unclear, that's totally OK. The takeaway here is we're varying the mass of the flag and seeing how that affects the results. The other term that we're going to vary is the stiffness of the flag, KB. And again, I won't go through the details of what these terms are. I just wanted to write them to be precise. But the idea is, in the numerator, we're taking the dimensional stiffness of the flag. So this is stiffness of the flag. And we're, again, normalizing it by some notion of stiffness in the fluid so that we can obtain this dimensionless parameter. So stiffness and flag, and we're going to stiffness and mass, and we're going to look at the behavior and how that changes with respect to these parameters. So to indicate to you how interesting this dynamical system is, and I think it's really, really beautiful, I'm going to show you what happens if we fix the mass and we vary the stiffness. So here we have for very stiff flags, so I'm showing you stiff flags, less stiff still, and the least stiff of all. And what happens is, for very stiff flags, as we have wind or some fluid moving from left to right, and then what we see is that the flag remains undeflected. So it stays in this position for all time. If we decrease the stiffness of the flag, then what happens is we start to see, I hope you can see this, there's some small amplitude flapping that the flag is undergoing. Whereas here, for stiffer flags, you don't see any flapping at all. So we're starting to see some qualitative changes in the behavior of the flag just by changing the stiffness. If we decrease the stiffness even more, then we see the large amplitude flapping that corresponds to that video that I just showed you. And decreasing the stiffness further takes us into a regime in which the flag is in a large deflection position, and it's undergoing small amplitude flapping about that large deflection position. So for me, this is what makes inverted flag flapping so fun and so interesting. Even from a qualitative perspective, just changing the stiffness of the flag takes you into completely different dynamical regimes that are completely different. And I'd like to highlight here for a second that the first work on inverted flags was done in 2013 in Professor Morteza Garib's group. And Cecilia was one of the members of that first study, and she's here with us. So I hope I can embarrass her a little bit by saying that. And so they were the first to look into the system, the first to realize that it's a very promising candidate for energy harvesting, and the first to identify all of these regimes. And so they were really a source of inspiration for us in identifying why this is such an interesting physical system. And so we really wanted to kind of run with that and ask ourselves a lot of questions about how we can continue to understand the physics of this better. So I think there are a lot of things that are interesting here, and I want to focus on two for today. The first thing that I want to focus on today is, can we describe these different regimes in a concise way, right? So what I'm showing with each of these figures, by the way, is a time lapse corresponding to the videos that I showed earlier. So you can think of this picture here as being an overlay of all of the snapshots from the video. And same thing for these other figures. So when we came up with these videos, what we did is we said, OK, we have a stiffness, and we're going to make a video, or in this case, an image that corresponds to that. So if you were to ask me, well, what happens if I change the stiffness to some other stiffness? Well, for that, what I would have to do is come up with a new image that describes that. And if you wanted another stiffness, I would have to do that again. And so you can see that it becomes kind of cumbersome and unwieldy to have a new image for every stiffness that we want to consider. And so our goal here is, can we convey all of this information on one figure? So that's the first thing that we want to do. And I want to argue later that this is not just concise, but it'll help us as a framework for understanding the physics of these systems as well. So that's the first goal for today. And the second goal is I want to look into a regime called chaotic flapping that was recently discovered by John Sader, who's at the University of Melbourne. He's a professor there, and by collaborators in Professor Gharib's group as well. So they're kind of key players here. So the chaotic flapping regime looks like this. So the flag starts down here, and you can see that it doesn't quite make it all the way up, so it comes back down. But then on the next go around, it actually is able to totally flop over to the other direction and come up. And then it can't quite make it down, so it comes back up. But then you can see on this next time, it generates enough momentum that it's able to swing over. And this one happened to be every other one. But if you were to keep watching this, it does this in a non-regular way, right? So this is truly chaotic. You can't predict when it's going to make it all the way across and when it's going to not make it across and come back down. And so this was recently discovered as a regime that is possible. And so it doesn't exist in any of those 4 regimes that I showed you earlier. It's something kind of in between. And we want to characterize this more carefully and try to understand some of what's happening here. And I'd like to say that what I'm going to show you from now on is work that Tim and I have been doing in conjunction with John Sader. OK, so our first goal is conveying this information in a concise way on a concise figure. And the type of figure that we'll be drawing is called a bifurcation diagram. So for those of you who know that, that's what this is. For those of you who don't, that's totally OK. We're going to build this from scratch. So on the x-axis, what I'm showing is 1 on kb, which is 1 on the stiffness. So as we move to the right on this plot, we are increasing the flexibility of the flag. And on the y-axis, what I'm showing is a quantity that I'm calling the tip displacement. So the displacement that I'm going to show is the y, or up and down displacement of the flag. And what I mean when I say tip is, if you look at this figure here, I'm looking at the leading edge of the flag. So the one that is the free end that's allowed to flap, right? So we're going to be trying to show quantities of this tip displacement as functions of stiffness that give us some meaningful intuition for what kind of flapping behavior we're seeing and what kind of regime we're in. OK, so one thing that we can draw on this bifurcation diagram quite quickly is there's an undeformed equilibrium, right? And we saw this in the first of those figures where it stays still even as the flow comes around it. So there's an equilibrium where this flag is undeformed. And what I'm denoting here is by the solid line, that equilibrium is stable. So as I come here, this is that undeformed equilibrium. And what that means is if I start with the flag deformed, and I start with fluid moving past that flag in a perfectly symmetric way, then it will stay there for all time. That is an equilibrium of that system. And that's what I'm showing here. And that's why you continue to see this equilibrium over here. It exists for any stiffness. If you, regardless of the stiffness of the flag, if you put it in this undeformed position and have steady, symmetric flow moving perfectly past it, it will stay there. And one thing that's really interesting, and this was again found by John Sader and Professor Gharib and their collaborators, is that for this range of stiffnesses, if it's sufficiently stiff, that equilibrium is stable. So what that means is if I were to come to this picture here and I were to flick it, then for this range of stiffnesses, it would come back to that undeformed position and stay there for all time. But at some point, as I decrease the stiffness, then if I were to go to this equilibrium picture and flick it, then it would depart that equilibrium position. And one thing that Tim and I realized recently, and we're really excited to find, is that as soon as this equilibrium becomes unstable, as soon as this position becomes sensitive to perturbations, then a new equilibrium pops up in which the flag is deformed. And so you can see that that corresponds to a non-zero tip displacement. And I think this is really neat because what happens here is for a small range of stiffnesses, I hope you can see this, that this line is solid. And so for a small range of stiffnesses, that deformed equilibrium is stable. So you can take the deformed equilibrium and flick it, and it'll come back to that deformed state as long as you're in this range of stiffnesses. But as you decrease the stiffness, then it becomes unstable. So this is not so surprising that we have unstable equilibria for a large range of stiffnesses, because as I showed you in those earlier videos, much of the behavior that we see is flapping behavior. So it makes sense that we're not going to see equilibrium much of the time. And just to show you what this equilibrium looks like for very flexible flags, I'm taking at this particular stiffness a very flexible case. There's a very large deflection equilibrium and a very large wake state associated with that. So as I mentioned, we see a lot of flapping in this inverted flag case. So how do we draw flapping on this bifurcation diagram? So I'm going to take this figure, and I'm going to completely litter it with a bunch of data, and we're going to walk through carefully how I did that. So here's the littered data, the littered figure. And what you can see is the same equilibria that I showed you earlier, but on top of that, we've got a lot of data points. And I'd like to just kind of like walk through a few of these to give you some intuition for how I built this figure. OK, so we're going to look at this particular stiffness where you see two dots, one here and one here. And what this regime corresponds to, just to ground you, is this large amplitude flapping regime that we keep seeing videos of. So we're going to show you how this regime leads to these two dots on this bifurcation diagram. And to do that, we're going to look at the tip displacement and tip velocity of our flag as functions of time. And what you can see, and this is maybe not surprising, is that after some transient period, the flag enters into a very regular periodic orbit, periodic behavior, with a fixed amplitude and a fixed frequency. And we saw that in the video, right? The flag is just very regularly, very periodically undergoing its flapping motion. So this makes sense. And so Tim and I scratched our heads for a while and thought, how do we want to represent this time trace data as just a set of points on this one line, at this one cross section? How do we do that? And so we thought, well, you know, for this particular regime, there's a very regular periodic flapping that's occurring. So something that would be a natural thing to plot is the peak-to-peak displacement, right? That gives you a lot of information. So we said, OK, we want to do the peak-to-peak displacement. And what I want to highlight is those peak-to-peak displacements correspond to places where the flag has a zero velocity, right? So I've got my flag that's coming up. It has a non-zero velocity, reaches its peak amplitude, at which point it reaches a zero velocity and starts to change direction. And then it has a non-zero velocity until it reaches the bottom, at which point it has a zero velocity and starts to change direction again. So we're looking for places where the tip has a zero velocity, and we want to take the displacement associated with that. And to show us what that looks like in a different way, rather than plotting tip displacement and tip velocity separately as functions of time, I'm going to show you a plot of the tip velocity as a function of the tip displacement. OK, so that looks like this. And just to talk you through that, this makes sense, right? As we're at our peak amplitude in tip displacement, so this is the largest displacement that we see, we're at a zero velocity. And that makes sense. We just talked about that. And then as we start to swing down, we increase in velocity, and we come down until we reach a zero velocity at the bottom, where again we've reached our other peak, and then we keep going around and around. And one thing that I want to highlight is it looks like there's just one curve on here, but actually I've plotted all of these cycles on this curve. And it just looks like one line because the behavior is so regular, right? This is a periodic orbit phenomenon that we're seeing. So again, what we're interested in is where the flag undergoes a zero velocity at its tip. And if I look at the displacements here and here associated with that, then I plot them on this curve. And that's exactly why you see these two dots here. Those are the tip displacements that correspond to a zero velocity of the flag. And again, I want to highlight that it looks like there are only two circles here, but there are actually several circles. They're just all overlaid on one another in the same way that all these lines are overlaid on one another. And so the circles here, there are many of them. They're just all on top of one another. So, you know, that's how we build that part of the bifurcation diagram. Let's look at one that's a little bit more interesting, maybe, which is the chaotic flapping regime. So if we look at the tip displacement and tip velocity as functions of time for this, we now see that there are breaks from this periodic flapping behavior where, say here, the flag goes up and down and up and down and up. And rather than going all the way down, it decides to come back up. And then it goes all the way down, and so on and so forth. So there are these breaks in the periodic behavior that we saw last time. And this, for me, really highlights why you don't just want to plot the peak-to-peak amplitude all the time, right? If we did that here, we would be missing a lot of information about the intrinsic dynamics of the system that we really want to be able to capture. And that, for me, as a follow-up, is why it's so valuable to not just take the peak-to-peak displacement, but to look at places where we have a zero tip velocity. because those are going to give us all the places where the flag is changing direction, right? And so now if we look at a similar plot to the one that we saw last time, where I'm plotting the tip velocity as a function of tip displacement, then now if I look at a zero velocity cross-section, I've got a much richer plane where the flag is changing direction, right? And that makes sense because we see it changing direction not just at its peaks, but at many other places in between as well. So we plot that on here, and we get this rich space of markers that fill that line. So we did that for all these various stiffnesses, and that's how we built this bifurcation diagram one by one. OK, so I want to take a step back and kind of look at what we did here in building this diagram. So there are a couple things that I want to say here. The first is we've conveyed all the information that I showed you for the different regimes on this one plot, right? And let's summarize that. So we've showed this undeformed state that exists and is seen for these very stiff cases. We showed that that gives way to this deformed equilibrium, which in turn, as we decrease the stiffness, ultimately leads to this small amplitude flapping regime. So I didn't show you how we got this, but you might be able to intuit that this small amplitude flapping corresponds to this case, right? And the way that you can see that is as it flaps, it's flapping, it never crosses this zero plane. And so it always stays about above the zero plane in a deflected state. And so it's undergoing amplitude, a small amplitude flapping that's always above the zero position. So that's why we're in this, that's why this is that regime here. We then talked about the large amplitude flapping and built that. We built chaotic flapping. And then we came here and looked into large deflection, small amplitude flapping. So I didn't show you this video yet, and I'd like to just highlight what this looks like. And my hope is that this is kind of intuitive when you see it on the bifurcation diagram, right? So we're always in a large deflection state, which is why all our markers are very deflected from this zero position. And we undergo small amplitude flapping, which is why the markers don't depart from one another very much, right? So we've been able to draw all of these regimes on one figure. But there's another thing that I really like about this figure, which is that I think it really gives us a framework to start to understand not just how can we convey these regimes concisely, but how can we start to understand how they react, what the interplay is between them, right? So here we know that there's this undeformed equilibrium that as you decrease stiffness becomes unstable and gives way to a deformed equilibrium. And that in turn becomes unstable and gives way to this small amplitude deflected flapping, and so on and so forth. So I think this bifurcation diagram is a nice mechanism for us to really start to try to understand the physics. And going back to our energy harvesting application, that's really important, right? We want in our energy harvesting application, let's say, to be in this large amplitude flapping regime. And so we really want to understand the mechanisms at play that take us from one regime to the other so that we can guide the design of technologies that keep us in the flapping regime that we want to be in. So, OK, that's bifurcation diagrams. That's why I think they're interesting. The last thing that I want to say about this is that we did this for one particular mass, and we varied the stiffness. And so I'll reproduce this figure here. This happened to be for a very light flag case, which corresponds to a very small mass. And we can do this for more masses, right? So we can increase the mass of the flag. So this is still less massive than the fluid, but slightly more massive. And we can increase the mass so that it's more massive than the fluid, and then substantially more massive than the fluid. And I won't talk about these in detail because I don't have time. I'd love to talk about it after. But there are two things that I want to say. One is, I think there's a really nice opportunity here, even qualitatively, to use these bifurcation diagrams to ask ourselves, how is the flapping behavior different as we vary the mass? I think this is a nice framework to ask that question. And the second thing that I want to highlight is, if we look in this chaotic flapping regime that we identified for this very light flag case, we see it persist here to some extent. But as we go into heavier flag cases, then if you look at this for long enough, you would be able to see and convince yourself that you don't have chaotic flapping anymore. So this is purely large amplitude flapping. You can kind of convince yourself of that if you look at it long enough. And that gives way directly to this large deflection, small amplitude flapping. So we lose chaotic flapping for this massive case, and that remains true for the very massive case. So one thing is chaotic flapping is a feature of light flags only. And I'd like to talk about chaotic flapping a little bit more. So to do that, we're going to look at this bifurcation diagram for the very light flag case that we looked at earlier. And when you do this, then the punchline here is going to be that it's not a coincidence that this chaotic regime is in between this large amplitude flapping regime and this large deflection, small amplitude flapping regime. And what I mean by that is if we look to the left of this chaotic regime into this large amplitude flapping regime, then you see this periodic orbit that we saw earlier. And if you look to the right of this chaotic regime, then we haven't seen this figure before, so I'd like to talk through it a second. So this is the large deflection flapping. And just to kind of convince ourselves that that's exactly what this is, you'll notice that for all, that the entire time the displacement is large. And that makes sense because we're in a large deflection state. So we have a large displacement and we're undergoing small amplitude oscillations about that large deflection state. So that's exactly this regime that we were talking about here. And then if we go back and look to our figure of chaotic flapping, then for me, this is a really wonderful picture of what's happening here, right? Chaotic flapping is not some completely random, completely uncharacterizable state. It's specifically a random switching between two states and two states only, right? We see here the existence of this large amplitude behavior that we saw to the left of this chaotic regime, and here, this small amplitude, large deflection behavior that we see to the right of the regime. So what is chaotic flapping? It's nothing but random switching between two very specific states. So that's one thing that I think is a fun realization. OK, so we've covered a lot of ground, and I'd just like to take a second to summarize what we did here. So the first thing is we motivated the study of these flapping flag problems by wanting to guide the design of future flow energy harvesters and by wanting to understand upper bounds for what the energy harvesting capacity of these systems is. So that was our motivation. We then talked about the mathematics associated with this and asked ourselves what is challenging about simulating these problems and talked about the idea that Tim and I came up with to simulate them efficiently. And then we looked into the physics of the system. And we first drew bifurcation diagrams that gave us information about the dynamics of this physical system and gave us a framework that we could start to ask about the physics for how these regimes interplay with one another. And then we identified chaotic flapping as a function of light flags only and not heavy flags. And within light flags, it is specifically characterized by random switching between large amplitude flapping and large deflection flapping. OK, so that's all I have for today. That was a lot, and I appreciate your patience with me. I'd like to just end with a few acknowledgements. So the first is I really want to give my thanks to the Everhart Lecture Committee and the GSC for putting this event on in the first place, and in particular for giving me a chance to speak here. It really means a lot to me, and I really appreciate it. To Tim, my advisor, despite your joke at my expense, I really have enjoyed having you as an advisor. And obviously, I've learned so much from you about fluid mechanics and computational mathematics. But to be honest, the thing that I'm most grateful for is you're a wonderful mentor. And I really mean it when I say that if I can be a fraction as good as you are at mentoring, then I would consider myself hugely successful. So I hope I have made him sufficiently uncomfortable that, that his joke at my expense was worth it. I also want to thank Tim's group, the CFPG group, in particular Felipe, who's helped me so much understanding flapping flag behavior. And to the rest of the group, I've learned very much about both fluid mechanics and computational math. And they've made Caltech and the Thomas Building just such a wonderful place to work in. So thank you, guys. Last, I want to thank Tess, who has been the most amazing partner and teammate in life and in academics. You're wonderful. And to speak to the specifics of this presentation, you should all know now that Tess is the best presenter that I've ever encountered. So anything that was right about this, frankly, came from both the feedback of the GSC committee, but also feedback from Tess, who is a phenomenal presenter. For funding, I would really like to thank the NSF for giving me money and also JPL for doing that. So thank you so much.